In lesson 7.5, partial fractions, we'll be revisiting the idea of partial fraction decomposition that you learned last year in pre-calculus. This time in BC, though, we're actually going to have a point for it. We're going to turn some rational function into a polynomial plus a series of easier-to-deal-with fractions for the purpose of integrating. Of course, integrating a polynomial and integrating a bunch of simple fractions is much easier than integrating some random rational function. So really, we're just rewriting a function in order to make it easier to integrate. Let's go ahead and take a look at a reasonable procedure to do this before we take a look at any of the examples. The first thing you want to do when performing a partial fraction decomposition is to ensure that your rational function is not top-heavy. What I mean by that is you need to make sure that the numerator is of a lower degree than the denominator. If in fact your rational function is top-heavy, the top is of a heavier degree than the bottom, then you certainly need to go ahead and divide the rational function. What you'll end up with when you do that is a polynomial plus an extra fraction that's simply the remainder of the division problem divided by your original denominator. Whether you divide or not, you will have a denominator that hopefully you'll be able to factor in the second step. And in this class, it will always factor into a series of linear or quadratic factors. It'll only be one of those two. Now, of course, it could be a lot of linear or a lot of quadratic factors. In fact, they could even repeat sometimes. But they will always only be linear or quadratic. So how do we deal with these? How are we going to split this fraction where the denominator is all these factors into a bunch of smaller fractions? Well, for each linear factor or repeated linear factor, we're going to assign a constant as the numerator. So we're going to create a numerator that is constant, and that will be for each linear factor or repeated linear factor. And I'll show you what I'm talking about with that. We could end up with something like this constant divided by the linear factor ax plus b. Perhaps there's another linear factor, we'll call it cx plus d squared. Now, even though it is squared, it's still a linear factor. It just occurs twice. And the way we would handle that, we would assign a constant to the original, which is cx plus d, and then we'll assign a separate constant to the repeated version of that. So there's your cx plus d squared. So that's how we split up all the linear factors. The quadratic factors are quite similar, in fact. The only difference is the numerator is going to be a linear binomial for each factor. So I'll put it's a linear binomial for each quadratic or repeated quadratic. And this is going to look much the same as step 3 here with the linears. It's simply we're going to use linear binomials for each quadratic factor. So here's the first quadratic factor. Maybe there's only one quadratic factor. It repeats, let's say. So we would end up with this then. Of course, every quadratic factor or repeated quadratic factor would get its own linear binomial, and then we would go ahead and start using some algorithms to break our fraction down to do a partial fraction decomposition. Our first example dealing with a partial fraction decomposition is actually quite exciting because this example can be solved 2 different ways. Now, regardless of which way we choose to do it, we're going to have to start the same way. Notice that this is a top-heavy rational function, so we will need to divide this. I'm going to leave the division up to you. So if you want to pause here and give it a shot, come back and check your answers, see how you did. If you choose not to do that, then I'll just go ahead and tell you that when you do divide this, you'll end up with x minus 1 with a remainder of x minus 1, which we go ahead and put over our original denominator. As you can see, integrating this would be a mess. I'm not quite sure how I would do it. Integrating this should not be too difficult of a problem. I got my remainder wrong, my apologies. There would be the remainder. So if I want to go ahead and integrate this, that doesn't really look too bad, except for this part right here, until you realize that this could be a u du substitution. Take a look at this, that would be the u. Du would, of course, then just be 2x plus 1, which is exactly what we have in the numerator. That's a perfect natural log integration. So we'd simply end up with 1/2 x squared minus x plus the natural log of x squared plus x minus 2. Now, you might realize that this does factor, and that being the case, the natural log of one factor times another is simply the sum of their individual natural logs. So I could turn this into the natural log of x plus 2, which is one of the factors, plus the natural log of x minus 1, the other factor. So here is our solution. We got this using no partial fraction decomposition at all. In fact, all we had to do was divide it and then realize that we had a natural log thing going on. However, I wonder how it would look like if we tried this problem one more time with a partial fraction decomposition. So here we are on the same problem again. I want to do it a little differently this time, but again, it will start the same way. It will start by dividing it, which will give us this, as we already saw earlier. However, this time, what I want to do is do a partial fraction decomposition to the remainder portion of my polynomial. This part here will still stand, the integral of x minus 1. So, we need to realize that this does factor right here. In fact, if I factor it, it'll factor into x plus 2 and x minus 1. What I want to do for each linear factor, which are x plus 2 and the x minus 1, I want to assign each of those a constant numerator so that it looks something like this. Now, if I go through and multiply by my x plus 2, x minus 1, that would eliminate all these fractions, and it would actually just leave me with 2x plus 1 on the left side. And let me actually show this here. So if I'm multiplying by x plus 2, x plus 1. Now for this term here, the x plus 2's would cancel, but I would still have x plus 1. And for this one here, the x minus 1's would cancel. My apologies, that should be a minus 1. So the two x minus 1's would cancel, and I would be left with an x plus 2b. Again, this should be x minus 1, so we'll see if we can fix that a little bit there. All right, well, there's a lot of different ways you can try to work out what a and b are in this case. My favorite way of doing it is simply to choose values of x that will cause these factors to zero out. For example, if x equals 1, on the left side, that would clearly just be 3. On the right side, this would zero out, and I would have 3b remaining. Clearly, b equals 1. Now, what should I choose for my other value of x to cause this term to cancel out? And that would be negative 2. So if x equals negative 2, on the left side, you see I'd get negative 3. On the right side, this would be negative 3a. And again, this would cancel out, which was the whole point. And doing a little bit of algebra there, we get that a is also 1. Well, this integral problem just turned into, check this out, the integral of x minus 1 as was already given, plus this ugly thing, which we just found out equals a over this plus b over this, with these values for a and b. That's 1 over x plus 2 plus 1 over x minus 1. If we go ahead and integrate that, I think it's fairly obvious to see that we're going to end up with the same answer that we ended up with previously. Of course, we did it a different method. And the partial fraction decomposition is going to work in a much more general sense. So I would get used to using this. And there we go, the same answer that we got before. So here's our second example of partial fraction decomposition. This is certainly a problem that looks a lot heavier, but I'm going to argue is really no different than the last one we looked at. The only real difficult part of this problem is factoring, and I'm going to leave that up to you to factor. However, if done correctly, you should end up with, of course, still just 4x squared in the numerator. But this should factor into two linear factors, one single and one repeated. That would be x minus 1 times the quantity x plus 1 squared. I'll leave that to you to see that that is, in fact, the correct factoring for that. However, that being the case, we can set up our partial fraction decomposition. If I rewrite this on the left side, remember each one of these linear factors and the repeated linear factor are going to get their own constants. So here's x minus 1 with its constant. Here is x plus 1 with its constant. And finally, here is x plus 1 squared, the repeated linear factor, with its own constant. Now, what I'm going to do to cancel out all the fractions is I'm simply going to multiply by the common denominator, which they all share, which you see right here. That is x minus 1 times the quantity x plus 1 squared. By doing that, on the left side, I'm simply going to end up with 4x squared. Here, the x minus 1 and the x minus 1 will cancel out, and I'll be left with x plus 1 squared times a. For my b term, the x plus 1 will cancel out one of the x plus 1s, leaving me with an x minus 1 and an x plus 1 times b. And finally, for my c, the x plus 1 squared will cancel the x plus 1 squared, leaving me with just x minus 1c. Now, just like in the last problem, I'm going to choose values of x that cause certain terms to cancel out. I'll start by trying to cancel out the a, and by letting x be negative 1, that will cancel out this term. As a consequence of that, this b term will also cancel out, and I'll just be left with c. This could be really nice. On the left side, I'll have 4. On the right side, this is gone, and I'm left here with negative 2c. Do a little bit of math, and you find out that c, in fact, does equal just negative 2. Another thing I can let x equal, I could let x equal 1. That would cause the c term to cancel out, and by consequence, of course, this b term. So that would be really good. If x equals 1, I have 4 on the left side. This will be 2 squared for my a, or 4a. Again, the b term cancels out because of this, and the c term cancels out. And I see that a must equal 1. Well, now I'm at a crossroads. I don't have another value to pick that will cause a and c to cancel out so I can solve for b. So what I can do is I can either substitute a and c back in. I can choose some other value and just hope that it works. There's a lot of different ways I could do this. Just for fun, I'm just going to go ahead and let x equal 0. By doing that, I'll get 0 on the left side. This will give me 1 squared a. 1 squared a. Of course, a is 1. So we have that. B I don't know, but this will give me negative 1 times positive 1b. So I'll have minus b. And if I plug 0 in here, I have negative 1c. But I know what c is. So this will say plus 2. Now, again, do a little bit of math here. And we'll find that b is going to equal 3. 3 if I'm correct. Yes. And there we go. So this craziness right here is going to break down following this partial fraction decomposition. What we're going to end up with is the integral of a over x minus 1. And here is a over x minus 1 plus b over x plus 1. So here is my b over x plus 1. And finally, c over x plus 1 squared. There's my c. And so that'll give me minus 2 over x plus 1 squared. Well, 2 of those are going to be very easy to integrate. The third is moderately easy. And let's see, what I'm going to end up with here is the natural log of x minus 1. I'm going to end up in this middle term with 3 natural logs of x plus 1. And then on this last term, it'll be much easier if you consider this to be negative 2 and then x plus 1 to the negative 2. If you think about it that way, it's going to be much easier to handle this one. When I integrate that, what am I going to end up with here? Negative 2 over negative 1, and I'll have x plus 1 to the negative 1. So it looks like this is going to end up being plus 2 over x plus 1 plus c. And so what started out as a real evil problem became really simple through the process of partial value decomposition or partial fraction decomposition. And there is my final result. Feel free to differentiate that and see if you don't end up with the original problem if you like, but trust me, it is correct. While we're not actually going to fully complete the third example of the partial fraction decomposition, I do want to get you started on this problem, and really I want to remind you of how to factor a difference of cubes. Yes, for the BC exam, you do have to know how to factor the sum and difference of cubes, so please do not forget those. In this case, to factor x cubed minus 8, we're going to end up with the factors x minus 2 times the quantity x squared plus 2x plus 4. If you do not remember how to factor the sum or difference of cubes, feel free to look that up. It's either back in your Algebra 2 notes. You can look online at any Wikipedia entry or anything really, but make sure you know that formula right there. Now, if we go ahead and do our partial fraction decomposition, you can see I do have one linear and one quadratic factor, so that will certainly make things really, really exciting. I'll end up with, well, here is my left side. I always start off by just repeating this. But then over here, for my linear factor, I'm going to assign a constant. And for my quadratic factor, I'm going to assign a linear binomial. I've already used a, so let me call this one bx plus c. Now, if I go ahead and multiply by my common denominator, which is simply the x minus 2 times the x squared plus 2x plus 4. If I do multiply by that, then on the left side, I'm just going to get 6x. On the right side, I'm going to get x squared plus 2x plus 4 times a. Of course, the x minus 2 is canceled out. And here, the quadratics are going to cancel out, and I'll just be left with x minus 2 times the quantity bx plus c. Now, just like in the last problem, I want to try to choose some values for x that will cause certain factors to zero out. The most obvious one, I think, is right here. If I let x equal 2, we'll see what happens. Of course, if x equals 2 on the left side, I simply have 12. On the right side, I'll have, if I plug 2 in here, I'll have 12a. And if I plug 2 in here, this zeroes out, zeroing out this entire thing. And I see that a is, in fact, going to be equal to 1. What's another value that will cause things to drop out? I really don't know. So what I'll do is I will just assign 0 to x and see how well that works. On the left side, it'll give me 0. On the right side here, if I plug zeros in here, I end up with 4a. All right, well, that's great. I know what a is, so 4a is just going to be 4. Plug a 0 in here, plug a 0 in here. That gets rid of the b, and I just have minus 2c. Well, I'll do a little bit of work there, and I think that you will find that c is simply equal to 2. All right, well, I'm on my way. I have, let's see, just one variable left. And for this last one, I'm just going to choose some random value. I'll choose x as 1, and we'll see how that works out. On the left side, if x is 1, I'll just have 6. On the right side, if I put 1 in here, I will have 1, 2, and 4, which is 7a. 7a, well, a is 1, so that's just going to be 7. Here I'll have 1 minus 2, so that's going to be a negative 1 and a bx plus c. But c is 2. So this is essentially going to be a negative 1 and a bx plus c. All right, well, I see that that's just going to be minus bx minus 2. And if we do a little bit of work here, we get that 6 is going to be 5 minus bx. Do a little bit more work. We're on our way. Subtract the 5. We have 1 equals negative bx. Actually, x is 1, so this doesn't need to be here. And we get that b is, in fact, negative 1. So, fantastic. This big ugly thing here is simply going to break down into the integral of a over x minus 2. So there is a over x minus 2. And then we'll have bx plus c over all this. So here is my bx plus c all over the x squared plus 2x plus 4. Now, this isn't a very easy integral to work out, and I'll leave it to you to work it out. Of course, this first part is easy enough. That's simply going to be the natural log of x minus 2. But I'll leave it as an exercise for you to verify that, in fact, the rest of this is going to be minus 1/2 the natural log of our denominator, our quadratic denominator. And then, of course, maybe it's not so clear, but if you work it out, you'll get square root of 3 arctangent of x plus 1 all over square root of 3. That's by completing the square down here. So that's what we end up with for that. It's not pretty, but it does work. And with that, why don't we take a look at our final example? It's a fun one, too. For our last example today, we'll take a look at a partial fraction decomposition involving a repeated quadratic factor in the denominator. There's really nothing to do to set this up. We already have that it is a proper fraction. The denominator is of a higher degree, a 4th degree, than the numerator. So we have nothing to worry about there. In fact, I'm just going to go ahead and start by setting this up and saying that this fraction right here, actually I don't need the integral at all, but I'm going to go ahead and say that x squared minus x plus 9 divided by the x squared plus 9 squared is equal to, well, here are the factors. We have x squared plus 9, and then we have the repeated quadratic factor, which is x squared plus 9 quantity squared. Each of those needs to get its own unique linear binomial. So we'll let that be ax plus b. This one can be cx plus d. And then all we'll do is we'll go ahead and multiply by the common denominator, in this case, x squared plus 9 quantity squared. What that's going to do, it's going to leave us on the left with just x squared minus x plus 9. Over here on the right side, this denominator will cancel out one of these, but it will leave the other. So we will have 1 x squared plus 9 to multiply by our ax plus b. This one, however, is the same as what we're multiplying by. They will cancel out, and we'll just be left with cx plus d. Now, in this situation, we can try substituting some values for x as we've done in the past. But there's no value of x that will cause this to zero out. We're not going to be able to get this to zero out completely. I can plug x equals 0 in. That'll still leave a d and a b. One thing I might want to consider is to simply multiply out the right side. Watch this. I'm going to get an ax cubed, which is fortunate. Notice that there are no cubes on the left side. I'm going to use that to my advantage. As far as my x squared terms, I'm going to end up with a bx squared, and that's going to be it. Which is fortunate. There's only an x squared over here. I can already tell what b is going to be here. As far as my x terms, I will have a 9ax. I'll also have a cx. So I will have 9a plus c times x. And finally, as far as my constant goes, b will multiply by 9. I also have a d. So it looks to me like my constant will be 9b plus d. Now I can start matching things up. Notice that there is no x cubed term over here. That tells me that a is going to have to be 0. It also tells me that this a is 0, but I'll get to that in just a moment. I have bx squared, which has to equal this 1x squared. I just figured out that b must be 1. That's fortunate. That means this b is also going to be 1. So if I take a look at my x, this is going to have to equal negative 1x. Well, fortunately, I already know what a is. A is 0. So this is simply 9 times 0 plus cx is going to equal this negative x. Well, I now know that c is negative 1. And finally, this term right here is going to be my constant. I already know that b is 1. So this is going to say 9 plus d equals the constant, which right here is 9. We just found out that d is 0. Fantastic. So this partial value decomposition actually ends up being rather nice. I'm going to end up with the integral of ax plus b over this. Well, ax plus b is just going to be 1 over x squared plus 9. And then my other one is going to be cx plus d. And there it is. All there is a negative x all over x squared plus 9 quantity squared. Well, so long as you remember your trig functions, you'll remember that this right here is simply 1/3 arctan of x over 3. That's not too bad. And I'll leave this to you to find out. If you do handle this one correctly, however, what you should find out is that this is simply going to be minus 1 over 2 times the quantity x squared plus 9. Again, I'll leave that to you to work out. Simply call this x squared plus 9 to the negative 2. You can stick a 2 in there for your du. And you end up with this as your final result of what looked to be a very confusing starting problem. It really wasn't all that bad. So, good luck with your partial fraction decompositions, and good luck with your 7.5 assignment.